Now that we have an idea that um, cyclohexanes can ring flip, and there are two different conformations, and that the hydrogens go from equatorial to axial, let's take a look at what happens when you put a substituent on the ring. So let's say we have methyl cyclohexane. Now, so far we've drawn methyl cyclohexane like this, right? We have um, a six-membered ring, and then we have a methyl group coming off of it. But we really haven't talked about the three-dimensional geometry of methyl cyclohexane. So now we can do so. And if we start drawing our chair, and we place the methyl group on the ring, notice we could place the methyl group in the equatorial position or on an axial position. So let's start off placing a methyl group on the equatorial position, and then of course we have the hydrogen that's on that carbon in the axial position. So this is an equatorial methyl group. Now, when we ring flip, what's going to happen? Remember, that carbon is going to go down, right? And so the what happens is, as you push that carbon down, now the methyl group goes axial and the hydrogen goes equatorial. So now we have an axial methyl group. Notice in both conformations, the methyl group is below the plane of the board. So the planarity, the relationship of the planarity never changes. It's always either above or below the plane of the board, depending on where you start from. So we start in the equatorial position below the plane of the board. We end up in the axial position, but still below the plane of the board. Now, in terms of stereochemistry, how are these two conformations related to one another? So again, recognize they are conformations. We didn't break any bonds or anything like that. We simply rotated about bonds. So that's what classifies something as a conformation. Um, so these are not mirror images of one another, but uh, they're not in the same spatial arrangement as one another as well. So we call these conformational diastereomers, right? They're not mirror images, so they're not enantiomers of one another, but they're not the same because they are in different spatial environments. So conformational diastereomers is what they are. Now, the other cool feature is if we think about whether or not there's a difference in stability between these two conformations. And of course, there is a big difference in stability. How do we know that? Well, in order to examine that, we have to think about the Newman projection. And when we look at the Newman projection, we can see the difference in the stability between these two conformations. Now, drawing the Newman projection of cyclohexane is something that we have to get used to. So, it takes practice trying to visualize things down various different types of bonds. So I'm going to show you two Newman projections of methyl cyclohexane in both the equatorial and the axial position. So let's start with the equatorial conformation first. So here I'm going to draw my equatorial methyl group, right, coming off of the cyclohexane ring. And I'm going to cite down the carbon that is attached to it. So this would be a C2 carbon. Now, if you think about what's on the C2 carbon, there are two hydrogens. One's equatorial and one's axial. So I'm citing down that bond, and then the carbon with the methyl group will be behind me. If I draw the Newman projection of that, I see the front carbon with that blue hydrogen, axial hydrogen, is pointing down at me. And so that's the carbon that I'm going to be looking at from the front. So I have this hydrogen pointing down, the blue hydrogen, and I have the blue hydrogen equatorial as well. And then on my left-hand side, I have part of the ring. So I have that methylene group that's part of the ring. Now, behind me, what do I have? Well, I have the hydrogen that's pointing up in the axial position, and then I have the methyl group that's in the equatorial position. And so I draw it in that angle. And then on the left-hand side, I have another methylene group, again, that's part of that ring, so I can connect by two other carbons, and I have now drawn the Newman projection of the methyl cyclohexane in the equatorial position. Now, one of the things to note is if there's any strain associated with it. So typically, when we think of groups and strain associated with them, we're going to be thinking about either eclipsed bonds, which in the chair conformation there are no eclipsed bonds, and therefore the only other potential energy strain that we have is gauche strain. And so we can look at the relationship between the methyl group and the rest um, of the cyclohexane chain, and we see that the only relationship is an anti-relationship, right? The methyl group is anti to that methylene group, and therefore there's no strain associated with it, right? So this is an easy way, the easiest way of looking at this particular molecule and drawing a Newman projection. I want to show you a little bit more complicated way of doing so, and of course there are many ways of drawing Newman projections. I could cite down that C1 carbon, having it in front. I could cite down the other C, I guess if you know C2 in this direction is C2 and the other direction are the same. So I could cite down this direction right here where I'm looking down this bond that I've highlighted in blue here. And that's a little bit more challenging. So let's see if we can do something like that. Well, we have to realize that, again, there are two hydrogens coming off of that particular carbon. And so when I'm citing down that bond, I see a hydrogen that is axial, a hydrogen that's equatorial, right? That's in the carbon that's facing me. And then the chain is on my right-hand side. Now behind me would be the methyl group is equatorial, right? And then the hydrogen is axial, and the rest of the methylene chain is behind me. So that's another way that I could draw this particular conformation. And again, notice we still see the same characteristic anti um, uh, R groups connected to one another. And so again, in this particular conformation, there's no strain. Now, why do I show this? Well, because there may be strain in different angles, right? So we have to think about all the various possible angles to see if there's strain. And if we look down the, obviously if we look down the C1 bond, I'd see the same scenario because it would be basically the same conformation, Newman projection, except it would be backwards. It'd be reversed of one another. So again, the take home is that in the equatorial position, there is no torsional strain because there's no eclipse bonds, but there's also no steric strain because the methyl is anti to the methylene group. Well, now let's take a look at the axial conformation. And so here I have the methyl in the axial position, and I'm going to cite down the C1 because it's right in front of me. So I'm going to cite down that carbon C1 C2 bond, and of course I can do the same thing, right? The two hydrogens, one's axial and one's equatorial, and then I can draw my Newman projection. So in my Newman projection, the front carbon is now C1. I have a methyl group, right? That's axial. I have the red hydrogen that's equatorial, and then I have my CH2 as part of the ring that is on the left-hand side. Looking at C2, the hydrogen is axial, another hydrogen is equatorial, and then I have the CH2 of the ring that is again on the left side of me. Now I'm highlighting one of the hydrogen bonds, and I'm going to talk about that in just a little bit. What I want you to realize is what CH2 group am I looking at? I'm looking, so notice I highlighted that CH2 in the red dot. One of those hydrogens is axial, it's pointing down, right? And so we're going to see that there's an interaction between that hydrogen and the methyl group as well. And so, of course, we have the other CH2, other methylene groups that attach that ring. Okay, so what do we have? Well, we have gauche strain. If you take a look, the methyl group is gauche to the ring itself, and so there's strain associated with that that gauche bond angle, right? So that's part of the strain, is that gauche interaction. The other thing is, notice, so I said I highlighted that hydrogen. Well, let's take a look at that a little bit further. So I have that hydrogen there. I have another hydrogen that is right here that's also axial. So when the methyl group is axial, notice it's going to interact with those two hydrogens. And that interaction is an electronic interaction. It's a steric effect. So I have a steric hindrance, right? That's associated with that. And we call this a 1,3 diaxial interaction, or a 1,3 diaxial repulsion, because they are repelling one another. Now, where do I get the 1,3? Well, if I consider arbitrarily naming one of the carbons with the hydrogen 1, then I get 2 and 3. So there's that 1 and 3 carbon interaction. So it's an arbitrary assignment of numbers. It doesn't really mean anything other than the relationship between the two hydrogens. One's on some arbitrary carbon number 1, and the other is on carbon number 3 relative to it, right? So there are two types of strains associated with the methyl group being in the axial conformation. One is that gauche strain, and the other is a 1,3 diaxial repulsion. Now it happens that the equatorial conformer is 1.74 kilocalories per mole more stable than the axial. We can measure that. But what does that mean in terms of equilibrium, right? Well, going back to basic general chemistry, we know something about energies, and we know that the Gibbs free energy equals the negative RT times the natural log of K. So that 1.74 is the free energy associated with the difference in the stability between the equatorial and the axial conformations. But it's related to K, which is the equilibrium constant. So if I know the R is a constant, right? It happens to be about 2 calories per degree mole, and temperature, T, is in Kelvin, then I can simply rearrange this equation. I can say that K equals E to the negative delta G over RT. So delta G is my the energy associated with it. And so it's very important to get the sign of delta G right, okay? So when it's positive 1.74, that means that we're going from the equatorial to the axial, right? That's a positive value. It's not spontaneous. If it were negative, that means that its axial is going to the equatorial. So we have to kind of be careful in our signs. And as a matter of fact, your textbook, I think, is a little bit I'll say wobbly on this. So keep in mind 1.74, that positive 1.74 means I'm going from the equatorial to the axial. And so what happens is when I plug this into my equation, I get e to the negative 1.74 divided by 0.002 times 298. And so I get a K of 5.4 times 10 to the minus 2. Your textbook does not have this because they've actually used the reverse of that. So it's a little bit confusing, but I want to kind of clarify what's going on there. Now make sure you can do this in your calculator because I might ask you to calculate K based on the difference in energy between two conformations. All right, so keep this in mind then. So K is 0.0054, right? Or roughly 0.005. Now, what does that mean? Okay, big picture, right? When I go from equatorial to axial, K, right, is the concentration of the axial divided by the concentration of the equatorial. And so oftentimes we'll write it up here, right? K equals 0.005. Well, I can also think of it in the opposite direction, that K equatorial axial is 1 over 0.005, so I've simply flipped it. And so if I take 1 divided by 0.005, I get 19. Now remember, this is a ratio. It means that I can think of it one of two ways, that for every 1 equatorial, there's 0.005 axial, but that doesn't really make a lot of sense. So I can inverse it and say for every 19 equatorial, there's 1 axial. For every 19 equatorial, there's 1 axial. So that makes a little bit more sense to me. In other words, for every 20 conformations, 19 of them are equatorial and only 1 axial. So for every one, it's important to understand how we get our equilibrium percentage, right? If there's 1 axial, 19 equatorial, then I can take 19 divided by 20, right, total. That gives me 95%. So, so at equilibrium, 95% of all conformations are equatorial. Now keep in mind that this doesn't mean that the once you have an equatorial conformation, it stays that way. They're all always flipping from equatorial to axial, but as a bulk, 95% of them are going to be in the equatorial position, 5%, only 5% in the axial position. So hopefully that makes sense to you, and you can kind of work on trying to figure out what that means. I know sometimes it's a little bit difficult going from energy to equilibrium. So another aspect of this is that larger groups actually have a greater dominance of that equatorial conformation. And the reason for this, now if you think about the strains, we have the angle, the gauche strain, and we have the 1,3 diaxial repulsion. Now gauche strain is what it is. It's independent really of the alkyl group. So all alkyl groups have about the same gauche strain. I mean, there's a little bit of a difference, but the big difference in energy has to do with the 1,3 diaxial repulsion. So when you have larger groups, you have larger 1,3 diaxial repulsions. We can take a look at an example where instead of having a methyl group, I have an isopropyl group. So when the isopropyl group is in the equatorial position, notice I can ring flip and get it into the axial position. Now in the axial position, right, if I look at this this equilibrium, I see that K is even smaller, 0.0012. And so if I calculate what that means in terms of percentages, I see that in the equatorial position, the isopropyl group in the equatorial position is 98.9% of the time. So only 1.1% of the time it's in the axial position. Why? Well, because those 1,3 diaxial repulsions that are happening, right? The isopropyl group is even larger, so I have even more steric strain associated with those two hydrogens. And I can even go one step further and put a tert-butyl group on, and I see that in the equilibrium between the equatorial and the axial, K for this is 8.4 times 10 to the minus fifth. That's 0.00084, okay? Which means in terms of percentage, 99.99% of tert-butyl cyclohexane is going to be in the equatorial position. And so you see very small changes in energy amount to very large changes in equilibrium distribution.